All right, let us start. So, good evening, everyone. I am Saptarshide, and this is the fourth week lecture video, a fourth week tutorial class for this course on Electrical Machines 1, arranged by NPTEL. I am a PhD scholar at IIT Bombay Electrical Engineering Department, and I work on machine design. And this tutorial is arranged weekly on Saturdays, 7 to 8 p.m. Today we are 5 minutes late, so we will end 5 minutes late. All right. So this week there were mostly three topics covered in the course, which are autotransformers, and two tests have been taught, which is polarity test of transformers, and the other one is Sumner's test of transformers. Okay, so these three are the topics which have been covered this week. We will first start with polarity test of transformers. So can you please confirm whether you are aware of the dot convention thing? Dot convention of transformers. No? Okay. So dot convention of transformer, or in a more general way, dot convention of coupled inductive circuits are meant for representation of the sense of winding of several. If there are more than one windings, if there is only one winding, then it doesn't matter. The dot, there is no sense of dot. Like here I have only one inductor, I put a dot here, it doesn't mean anything, meaningless. But when you have a coupled inductor, say that can be more than one, more than two also, but has to be at least two. Then the sense of the windings matter. So what do we mean by sense of winding? Sense of winding means, suppose I have a current flowing through this winding, and this current is an increasing current. Okay, say a ramp of current flowing like this. Then in this terminal, what will be the polarity? Will it be like this or will it be like this? That depends on how the windings are arranged on the core. So this is the basics of polarity test of transformer. And polarity test of transformer is required when you need to connect connect two or more than two transformers in several type of connection, maybe in three phase or maybe in parallel operation. So let me draw windings like this. Say I have one winding like this, okay, and say I have another winding like this. So can you see here that the sense of these two windings are different, right? Now, suppose I have a current I flowing in this direction, DC current, let us say constant DC current, I flowing in this path. Can someone please confirm in this arm, say, I mean in this region, how will the flux flow? From my left to right or from right to left?
Flux is never flowing, sir.
Why? In this iron core, there will be no flux?
It will flow, sir. It will flow, but in one direction only.
Which direction? I'm asking that.
Left and left to
right.
Sorry, one by one, please.
Forward direction.
Forward means on this top branch, left to right or right
to left, sir.
Right to left?
So left to right.
left to right.
Left to right,
Yeah.
sir.
Left to right. You have to apply the right hand screw rule. So it will flow left to right in this fashion. It will flow. But the thing is, this flux is constant. Why is this flux constant? Because this current is constant. So what is the EMF E that you will get in this situation in the secondary side of the transformer?
No EMF produces, sir.
No EMF produced because E is d psi dt and I have a constant flux, so there is no EMF produced. Now, suppose instead of having a oh, instead of having a what is that called? Just a minute. It's no problem here. Having a constant current, I have an increasing current. Okay. So now my current is like this. It is increasing, flowing in this direction and increasing. Now what is happening? You see this flux phi is increasing and this winding looks a flux phi downwards and this flux is an increasing flux. So can you tell me in what direction will it produce EMF? Like this EMF E, the polarity that I have shown here, with this, will the EMF be positive or negative? Can you say? Okay, let us do it in. Tell me, how should I approach with this? Which law should I use here to understand the direction of EMF?
Right hand thumb rule, sir.
Right hand thumb rule, what way? We have to use Lenge's law. Lenge's law. See, the flux is going down and it is increasing. So this winding will try to create a flux which is opposing this flux, that is upward. So this winding will try to create a flux that is upward. So this winding, if say some resistance is connected or some load is connected, will try to induce a current which is flowing like this, right? Can you see? Let me change the color, it will be easier, I think. See, this will try to create a current in this fashion, right? Then only we will have a upward flux from this winding. That is, we will get an EMF of this polarity. So if I have a current increasing, I will get a negative EMF. I should not say negative EMF. I will have an EMF of this polarity on the secondary side. Now we will see what is dot convention. See, dot convention is relative. So when you are starting giving dot convention, you have to give a dot in any winding first. Okay, doesn't matter where you give. I could have given it in here also. I am giving it here. Now with this, I have to give dot convention to the other windings. How? So the thing is that if the current entering in dot, a current entering in dot is increasing, then the positive potential of all other windings will be dot. So if the current entering the dot terminal of one winding is increasing, then the positive potential of all the other windings will be dotted. So here the current entering the dot was was increasing. So we got positive potential here, so the dot will be here. So once we have this, this is called the dot convention, and when we are doing polarity test of transformer, what we are doing is nothing but finding out these dots. Now see, I could have done it the other way also. Say, instead of giving the dot here, I give the dot here. So what do I have? I have a current which is going out. A current which is going out, and this current is increasing, right? So current going out increasing is nothing but current going in decreasing, right? It is nothing but di dt with direction, di dt with direction. So if I have the opposite here, now I have a current which is going in the dot and decreasing. So my negative terminal, or where I am getting the negative potential, will be now termed as dot. So I will have dot here. So you see, it doesn't matter whether I give dot here and here. Say I am naming this A, B, C, D. So whether I give dot at A and D, or whether I give dot at B and C, it doesn't matter. Both of them represent the same thing. They represent the same thing, but I cannot put dot at A and C. That is wrong. I cannot put at B and D. That is wrong. B and D I cannot put. That is wrong. But AC dot, putting the dot at A and D or putting the dot at B and C, they're the same thing, right? They are relative. Say you have another winding like this, and you have been asked to find out the dot convention. Where it will be? You will see it will be here. What you have to do, you have to simply assume, say I have given the dot here. So just assume that there is an increasing current through it. An increasing current through it will produce of increasing flux in this direction. And hence it will create a positive terminal here. So the dot will be somewhere here. I mean somewhere means in this terminal will be the dot. In this way we get the dot convention of coupled inductors. Now when we are doing polarity test on transformer, what we are doing is nothing but, we will look at the problems later, is nothing but the finding out the dot convention of the transformers. So say this is one transformer, right? Now this is kept inside a box, and transformer has a shell outside, then it is dipped into transformer oil. You can open it up and see inside how the windings are out, but you have to know the positive and negative sides. Not positive, negative. See, we are not giving plus minus. It doesn't matter where is plus, where is minus. That is why the convention is dot. So how to find out? The thing is, we short circuit one side and we apply an EMF E1 here. Now suppose the transformer has a turns ratio of E1 by E2. So a voltmeter which is connected here will read E2. But the question is, what is the polarity of it? One easy way, not easy way, you have to have resource for that. You can connect one oscilloscope and find out E1 and connect another oscilloscope. Say connect the oscilloscope here and here in this way. That is a probe here and the ground here. And if you find that E2 is in phase, so this is dot, this is dot. But you may not have this facility. So an easier way is you connect another voltmeter here. You connect another voltmeter here. Right? Now, when you are connecting another voltmeter here, if they are at the same polarity, see, I have already grounded them here, right? So the polarity of this point and the polarity of this point, both are being measured with respect to some common point. If I do not connect this, then both of the points are floating. Then the voltmeter can read anything. That doesn't make any sense. Or maybe it will not read anything because there is no path for current to flow through the voltmeter. It will not read anything. It is floating. That is why I will need this connection. These two shorting I need. Now once I need this, if I have them at the same polarity, not the same polarity, if I have the polarity plus here and also plus here, then the voltmeter is simply reading the difference between them, E1 minus E2. So I can understand that the dots are here. And if it's the opposite, I don't know from outside what is the polarity. If it is the opposite, if the dots are like this, then the voltmeter will read E1 plus E2. Okay, this way. Now, my question to you is, suppose I have a transformer which is rated as 200 by 400 volt, and on the transformer I want to do this polarity test. Can you tell me what should be the rating of this voltmeter? What rating voltmeter or what range of voltmeter should I use here? Should I use a 50?
200. 200.
200? Okay. Someone else wants to try? See, the readings could have been 400 minus 200. The readings could have been 400 plus 200. I don't know. We don't know beforehand where we are connecting. So we have to go for a 600 volt voltmeter if we are doing this test at rated voltage. Polarity test does not matter whether you do it at rated voltage or not. All you need to see whether you are getting additive or subtractive voltage. Okay, so that's about polarity test. Why we need polarity test we will see in the next week lecture. There you will see parallel operation of transformers. Now the next part that was covered here is Sumpner's test. Anyone aware about this Sumpner's test? Studied it somewhere else, not necessarily in this course, in university or wherever?
Back-to-back testing.
Back-to-back test, yeah. Why is it done?
For two identical transformer we are doing, sir, for temperature rise.
Yes, Sumpner test is done for temperature rise. But can I not, so why do I need two transformers? I will have only one transformer. Then I will load the transformer with its rated load and then find out the temperature rise. Why do I need a Sumpner test? Why do I need another transformer? Can I not simply load it with full load and find out the temperature rise? I run it for some hours.
Losses will more, sir. We have to give a rated voltage and rated current will be there. No?
Okay. What loss will be more?
Iron losses and copper losses, sir. Iron losses.
No, the transformer is operating at its rated condition. Why will the iron loss be more? Iron loss will be rated. Copper loss will be rated.
So more losses coming, sir. If we use rated current, means more losses come. That's why we are doing this.
No, if we are giving rated current, then we have rated loss. Rated current will give you rated loss. Rated voltage will give you rated copper loss. Rated can give you voltage give you the iron loss, and rated current give you the rated copper loss. The thing is that among with losses, we are also supplying the load. Losses is not more. Losses are at the rated value, but I have load. Say I have a megawatt transformer and I want to test it for temperature rise. So I have to connect a megawatt load to the transformer for several hours. That is why the Sumpner test is required. So what does Sumpner's test do? Basically, it is nothing but two transformers, identical transformer. This transformer supplying power to this transformer supplying the same power back to this. So if they were identical transformer, this thing would have gone forever. Power is flowing like this, but they are not identical transformer. There is loss. So conservation of energy says, so there should be some power source. So this power source is supplying only for the rated loss into 2. Right? So now we need not draw a megawatt power from the source. All we need to draw is this 2 times the loss, which may be in terms of some tens of kilowatt. So we have saved a lot of power. If some of you have already studied And if not, no worry, you will study at the end of this course. There is something called Hopkinson test. Hopkinson test is done in DC machines, and it is the same concept. Two machines, one motor, one generator, each feeds one another, and they only draw the loss from the supply. That is the idea behind this. So this is why we need Sumpner test to find out the temperature rise. Because see, if you do open circuit test, you will get only core loss. If you do short circuit test, you will get only copper loss. But the temperature rise, if you want to measure, you have to have both the losses occurring together. So you have to have rated voltage and rated current at the same time. That is why the Sumpner test is required. We cannot replace the Sumpner test with short circuit or open circuit tests. Now, you want to have some idea about how Sumpner test is done, or okay, looks like you have not. See, if you do not watch the videos, these sessions are useless. These are not alternatives to those. These are not substitutes. These are, how to say, supplements, not substitutes. Here I am here only to discuss your doubts. Since you are not watching videos, you don't have doubts, so I have to discuss these things. Okay, so what happens in Sumpner's test? You can anyone can ask doubt if you have any time. Okay, you can interrupt me and ask. So in Sumpner test, what we have is two identical transformers. Okay, very soon we will see why polarity test is required in transformer. Why do we need to? So let us say their dot conventions are like this, right? So what is done is the primary windings are connected in parallel. So Shidhar, please mute yourself.
No, regarding,
Okay, go on.
one minute, just regarding that polarity test, is it necessary to apply full voltage, primary voltage?
No, that is not required.
We can apply small voltage now, no?
Yes,
Small
yes,
voltage.
yes. If you have a KV range transformer, you can go for 100, 500 volt. But that shouldn't be very small, okay, because the transformers are not ideal. So there is some loss, some voltage drop in its, what is that called? Windings.
No,
The
but,
impedance.
for polarity test, just to know the polarities in primary.
Yes, that is enough. You can
Small, just 50 volt we can apply. Okay, thank you. Thank you, sir.
Okay, so in Sumpner test, we have two transformers whose primary are connected in parallel. Okay, I will just. Whose primaries are connected in parallel in this fashion, and they are receiving a supply from a voltage source. There will be one wattmeter also. This is the wattmeter. This is the supply voltage. So let us say it is connected here and it is connected here. Okay. And the secondaries are connected in anti-parallel fashion. That is, it's connected in series like this. Just a minute. If the current flows like this, suppose the current flows like this, it goes like this, it goes the opposite. Yeah. So their secondary is connected like this. Okay. They are identical transformers. Now suppose if I have voltage V1 here, the voltage that is coming here is V1 and the voltage that is coming here is also V1. If both the transformers have a turns ratio of V1 by V2, then I have V2 here and I have V2 here. So if you start traveling from here, you see there is a voltage up by V2 and there is a voltage drop by V2. So in this situation, if you connect a voltmeter here, it will read 0 volt. So, and not only that, instead of connecting a voltmeter, say you connect the voltmeter first. Sorry, my OneNote crashed. Just a second, my OneNote crashed. Okay,
Yes, sir.
all right. So what we have here. So here, if we what we do first is we first connect a voltmeter and see whether the voltage is 0 to make sure that we have connected the secondary in a proper fashion. Then once we are sure that we have connected the secondary in proper fashion, then instead of the voltmeter, what we can do is we can simply short circuit these terminals and there will be no current flowing through it, because anyway the voltages are opposing each other. Okay, so things are opposing each other, voltages. Now what is done is, instead of short, no, it is not short circuited. In Sampner test, what is done is we have a variable AC voltage source that is given by a variac. I am not drawing a variac, I am just drawing a variable AC voltage source. Okay, and I will have a, okay, let me draw the wattmeter to avoid confusion. I will have a wattmeter here. So wattmeter means a current coil and a pressure coil. So this is wattmeter 2 and the previous one was wattmeter 1. Now this voltage is varied. Shit. What is happening? Sorry for the problem. Now, what we are doing is we are varying this voltage. How much? Such that these two windings carry the rated current. Now see, there is nothing in this loop. We have simply short circuited two windings and we have supplied a voltage. So so a very small voltage here will give rise to the short circuit to the full load current, same as the short circuit test. Now, if you have full load currents, say I am writing I2, I2, if you have full load currents flowing in this fashion from undotted terminal to dotted terminal, you will have full load current in these terminals also. So here I have undotted to dotted here also, so the current will be here I1 and here also. No, sorry, this was wrong. I want you people to be vigilant at least. So I2 was flowing like this. So if I2 is going in this way, it is coming in this fashion. I2. See, they are connected in series. This fashion. So dotted to undotted, it will flow. So by transformer action, I1 will flow like this. Now, if you track the path of I1, so I1 goes like this. Here you see the same current I1 is flowing. So basically this I1 is flowing in this loop. It is flowing in this loop. Right? So the primary winding is drawing full load current at rated voltage, but they are not drawing the current from the supply. On the other hand, the secondary are at full load current, but at a very less supply voltage. So they are also not drawing much much of power. Now, if we look at it, see, before connecting this supply voltage, before this is sometimes called the auxiliary supply. So before connecting this auxiliary supply, we had these terminals open. So this wattmeter W1, this measures 2 times the core loss. And when we are doing these things in the secondary, we are connecting a variable supply voltage, connecting an wattmeter and all, and whatever current is flowing here. During this time, the excess current that induced in this primary, they did not come from the supply. That was revolving here itself. So we are not drawing any current from any power. The load current, we are not drawing from the supply, but still the transformers are operating at full load current and rated power factor. Sorry, full load current and rated voltage. Full load current and rated voltage. But they are drawing what? They are drawing only the losses. So this wattmeter W1 is supplying the copper loss. After connecting all these things, this current did not change. We have proven. So the short circuit power must be coming from 2. Short circuit power means the copper loss. So what we have to do is in subnet test, we just look at the wattmeter 1 and wattmeter 2 readings. They are 2 times the copper loss and the core loss, and at the same time, if we leave the transformers in this fashion, we will be able to find out the temperature rise at full load. But we are drawing only the losses from the source. So this is the concept behind subnet test. Any doubt with what we have discussed till now? No doubt?
At the same instant, we are connecting W1, W2 only, sir.
Yes.
First, we connect the W1 and then the secondary open circuit. After that, we connect to W2 and
Yes.
then connect like that, sir.
Yes. And you see continuously, W1 will always, whether you connect W2 or not, W1 is always measured the copper loss. Sorry, will always measure the core loss. This one, because it is operating at full voltage. On the other hand, W2, which is carrying the full load current, it will always measure the copper loss. The losses are decoupled, not only decoupled, they are happening together, which we do not get in our short circuit and open circuit tests. This is why we need to do subnet test, and you also got an idea why polarity tests are required. See, without polarity test, you cannot even properly connect the transformers. You do not know which terminal to connect where. In the next week's lecture also, you will see that suppose you have 11 kV line, the high tension lines that come to your locality or my locality or 11 kV line, and they are stepped down to 400 volt. Okay, 3-phase. I am drawing single phase, though they are 3-phase. And say one transformer was there previously, some transformer which you see the transformer from your childhood maybe. That was there for a long time. Now several new flats, apartments, houses keep growing in your locality, and there is much more load requirement. This one transformer cannot supply. What the electricity company will do, they will come, erect another pole, and then connect another transformer. I think all of you have seen this, installing new transformers in your locality. So in these cases, you cannot connect them in any matter, in any way. So if you have dot here, and if you need to install dot, so suppose the new transformer that you have given dot here on the lower line, so you have to give dot here also. So I'm not saying that you have to give dot. The transformer, that new transformer that comes with the dot convention painted on it. Looking at the dot convention, you have to connect the transformer such that the arrangement is like this. Is it clear? You are not giving dots. The transformers come with the dots painted on it. Okay.
Okay, sir.
And another part that was taught here was autotransformer. So you have any doubt from autotransformer? Anyone has any doubt from autotransformer lectures? No doubt.
Hello. Hello, sir.
Yes, go ahead.
The auto transformer, if the secondary windings are instead of subtractive nature, considered in subtractive nature, so such type of discussion was not made by the professor.
Okay. So, maybe you are talking about let us say we are using a single phase regular transformer as auto transformer. Let us say it is a 400 by 200 volt transformer. Okay, so subtractive means what do we need to do? This is 400. So if I apply a 400 volt in this direction, there will be a 200 volt in this fashion, right? Let us take not 400, 200, let us take 400, 100, okay? Otherwise, things will look confusing. 100. Now, out of this, I want to derive a 400 by 300 volt transformer. I have the 400 already here. Now, how to get the 300? So, say it increases like this and it should drop. So, if I connect it in this fashion and then if I connect a load here, what we will see from here to here, 400 up, 100 down. So here across this load, we have 300 volt. So if we apply a 400 volt supply here, sorry, if we apply a 400 volt supply here and make a connection like this, I will erase the unnecessary parts. I will have the transformer windings connected in subtractive manner. You see here again, the dot convention has become important. So once we have drawn this, say in my calculation, I find out, okay, I have to connect like this, then I have the actual transformer where the dot conventions are painted. Question will come, see this is the 400 written on the transformer. So I know from my drawing that I have to connect this winding with this winding. I have to give the supply here and I have to connect my load in these terminals. This is again the dot convention is in this way important. So that is the connection, and analysis point of view is the same. It doesn't matter what kind of transformer it is. Analysis point of view, everything is same. The analysis does not change. Clear up to this? Anything else, or we will move to doubts? Problems. As many as we could do for today. Okay, so let us look at this problem on auto transformer. So it is a three-winding auto transformer, which is loaded in show as shown in figure. There are two loads connected. You see, basically, what they have done is there are three windings. So there is some core, and there are three windings connected like this. Okay, not necessarily auto transformer, connected like this. Polarity test has been done, and then the windings have been connected in this fashion. Then there is a supply, there is a load. The question is, load 1 consumes 750 kVA and load 2 consumes 200 kVA. All the loads have unity power factor. And they have given the voltages 600 volt. So this is 600 volt. V1 is 300 volt. This is 300. And V2 is 300 volt. This is again 300. So if this is 300, this is 600, this will also be 300. From the dot convention we can say that it is 300 like this, 300 like this, 300 like this. Okay. Is it clear how I got 300 here? KVL. It is 600 volt here. With 300, 300. So the question is, estimate the current in ampere in section AB. In AB, enter a positive number. Okay, whatever. So we have to find out the current in AB. And in the other questions is current in BC, current in CD. So basically we have to find out the current in these three sections. Now, how to find out? Can you help? Where to start with? Can I find out this current? This current can I find out? See, the load 1 consumes a voltage of 700 kVA, right? And it is at unity power factor. What is the voltage across load 1? What is the voltage across load 1? I would expect this answer at least, the voltage across load 1. Am I audible?
Yes, sir. 600 only, sir.
600, how do we get 600? Load 1 is connected here and here. So 300, 300, 300, 900 volt. So if I call this current I1, so this will be 700 kVA or 700 kilowatt, it is unity power factor, divided by 900 volt. So whatever you get, that much current will flow in I1. Okay. So can someone tell me how much are you getting? I am writing some value. It will be around 777.8 ampere. So this much of current is flowing here, 777.8 ampere. Now the next question is, estimate the current in section BC. How to find out? There are two loads. One load is consuming 700 kilowatt of power. Other load is consuming 200 kilowatt of power. So there is in total 900 kilowatt of power. Now this power is coming from this source. Right? All of them are at unity power factor. So the source current, if I write as IS, the source current that will flow, it will be 900 kilowatt divided by 600 volt. It will be 1500 ampere. So I have 1500 ampere coming here. I have 777 ampere going out. Can someone tell me what will be the current in the branch BC? How to find out? What is the rule? What is the formula? What is the principle? How to find out the current in BC? We know this current, we know this current. What law?
KCL.
KCL. Then what minus what? Or what plus what? I have to find out the current in BC in this direction.
IS minus I1, sir.
IS minus I1. So basically IS is going in different two parts. So you have 1500 minus 777 ampere. Whatever you get, that is the answer. Okay. Let us not concentrate much on the numbers, okay? Although numbers are important, but here we are trying to understand the concepts. Okay. Now the third part asks, estimate the current in ampere in section CD. What will be the current here? Same thing. The power of load 2 consumes a power of 200 kilowatt and it is operating at 300 volt. So it will be 2 by 3. Should be 666 or something. Yes, 666.7. So if I am right, so okay, I did not write, so I write it, say I2. This will be I2. So if I write it I3, this is I3. And this is nothing but I1. So I3 is 666.7 ampere. Sorry, this is not I3. I'm wrong. This is not I3. This is the current drawn by the load. This is the current drawn by the load. We know the power consumed by the load 2, which is 200 kilowatt, and the voltage across it is 300 volt. So the load is drawing this much of current. So I3 is here. I3 is here. So this is the current drawn by load 2. Now I2, some 723 ampere was coming down. Out of it, some 666 ampere went away. The rest will be flowing through this winding CD, which is 723 minus 666. 57 ampere will be flowing. Okay, instead of writing 57 ampere here, let me write something else, I4. So I4, which is the current through current through CD, is 57 ampere. Any doubt in this whole problem?
No, sir.
If not, then we will look at one more problem. A 125 volt by 100 volt single phase autotransformer takes 16 ampere current at 0.2 power factor when the low voltage side is shorted and the high voltage side is connected to 5 volt supply. So the low voltage side is the secondary side. So we have the transformer like this. is a 125 by 100 volt transformer, and the low voltage side is shorted. So what happens is, in a short circuit test, we short it through an ammeter, and we have another ammeter here and a variable supply. So what we got?
Sir, it's audio problem, I think so, sir.
Sorry, go ahead. Could you please repeat?
Sir, you are in mute, sir.
I am on mute.
Sorry, you are audible.
I am audible, right? I am not on mute. Okay, so I think there is some problem with your audio. So this is the short circuit test arrangement, and what we got is, it is taking 16 ampere current at 0.2 power factor at 5 volt supply. Okay. So what we have to find out is, we have to find out the impedance of the transformer.
Sir, you are in mute, sir. You are not audible to you.
Others can listen to me, right? Because I can see that my audio is coming.
Yes, sir. You are audible.
Okay, it looks like you have some problem with your audio. You can rejoin the meeting. Could someone please tell him in chat to rejoin the meeting? Someone asked me something in the chat. I forgot. Okay, we'll see. So we have to find out the impedance, because short circuit test, could someone please tell him in the chat to rejoin? Okay. So what we have is, we have from a 5 volt source, we have 16 ampere of current at 0.2 power factor. So what is the short circuit power? The short circuit power is 16 ampere into 5 volt into 0.2, which is 16 watt. So we are so in short circuit test, the transformer is drawing 16 watt. So what is the 16 watt? This 16 watt is nothing but the copper loss of the transformer, right? So I squared R is 16 watt. What I do we have? We have 16 squared into R, which is 16. So R we have 16 by 16 squared, this much of ohm. So 16 inverse will give you 0.625 ohm. So this is the total winding resistance of the transformer as seen from the high voltage side. Okay, we are doing this test at the high voltage side. Now we have to find out X. We have to find out X. How to find out X? We have been given the power factor 0.2. We know that omega L by R. Let me write it here. Tan inverse of omega L by R. This gives us the phi. Phi is cos inverse 0.2. Right? So from here, can you find out L? Can someone do and tell? So tan of cos inverse 0.2 L should come as 3.06. Could someone please confirm? Not L, XL. We need not know L. XL, which is nothing but omega L. So, when referred from the primary side or the high voltage side, the impedance as seen from the high voltage side is 0.625 plus J 3.06 ohm. This is it. Now the question is, high voltage side is connected to 125 volt, that is its rated voltage, and the low voltage side is drawing 45 ampere of current at unity power factor. Estimate the voltage drop with respect to the rated or no load voltage. Now, before going into this, can you tell me what is this thing called that when I am loading a transformer, the secondary voltage drops? So I had the load here, the switch was open, I got the rated voltage. Now, as soon as I connect the load, the voltage here drops. I get a voltage which is somewhat less or more than the rated voltage, more also. So what is this phenomena called? Is my question clear? When I am connecting a load in a practical transformer, the voltage changes. When there was no load, say there was 400 volt, I connect the load, the voltage becomes 380 volt or maybe 420 volt. What is this phenomena called? This is week 4. If you cannot answer this question, means you have not yet watched week 3 videos also. This was discussed in week 3. This is called regulation. Voltage regulation. So we have been asked to find out the voltage regulation. Now there is a formula for voltage regulation. The formula for voltage regulation is I2 R2 cos theta 2 plus I2 x2 sin theta 2. Theta 2 is the load power factor. Right. So what we can do here is, in our case, in the question, if you see, it has been mentioned that unity power factor. So in our case, cos theta 2 is 1, sin theta 2 is 0. So in our case, it is just I2 R2. Okay. Divided by V2 gives you the, what is that called? Per unit voltage regulation. I am talking about voltage regulation. See, if you see the dimension IR, IX, these are dimensions of voltage. If I divide it by secondary voltage, it becomes dimensionless, that is per unit voltage regulation. But here we have been asking the question to find out the voltage drop. So you have to find out the voltage drop magnitude. So what is I2? It is given, it's 45 ampere. And can someone tell me what will be R2? Can someone please unmute and tell me what will be R2? It is a 125 by 100 volt transformer. Well, no response. Week 1 question. This was a week 1 question. 3.06 times 100 by 125 squared. This, whatever value you get, that much will be the voltage drop. Someone please do it and tell me the value. Now, if you have seen the derivation process of this thing, of this equation, you will see that this is actually an approximate equation, not the exact equation. So how to, so in this case, we can also find out the exact voltage drop. So whatever voltage drop you get here is the approximate one. We can easily get the exact voltage drop also. For that, what we have to do is say we have the transformer. Now, we have referred Z in secondary. Okay. So we had this Z in high voltage and we have referred to it in low voltage. Low voltage Z will be 100 by 125 squared Z high voltage. This Z low voltage we can find out, R2, X2. And there is 125 volt. Now since there is 125 volt, I have 100 volt induced here. Right. So I have the simplified AC circuit has 100 volt here. This voltage we do not know, we have to find out, but the current we know. 45 ampere of current is flowing, and we have the values of R and X. We have the value of R and X. Now, if you just assume this to be the reference phasor 45 angle 0, you multiply it with this impedance, you will get the voltage drop, and hence you will get the voltage here, which will be less than 100 volt. The difference will be the voltage regulation. Now, how to find out this? These are even lower class things. 45 angle 0 times R2 plus JX2, or you can do it as Z angle theta, theta impedance, something like this, let's say. You can find it out from here, right? Z is root over R squared plus X squared, and theta will be tan inverse X by R. You can find out the voltage drop. So whatever voltage drop you have here is nothing but the voltage drop, the voltage regulation. Now the next part is the secondary side has 35 ampere current at 0.75 lagging power factor. Same thing. Nothing has changed. Only thing is that if we have how much? 75 lagging power factor. So you have, sorry, I forgot the current value. 35 ampere. So 35 into 0.625, we already seen this, into 100 by 125 squared into 0.75. This is cos theta. What we are doing is I2, this is R2 cos theta plus I2 X2, X is 3.06 into 100 by 125 squared. So I2 X2 into sine theta. Sine theta will be 1 minus square root of 1 minus 0.75 squared. So whatever you get, that will be the voltage drop, the voltage regulation. So here the power factor is not unity. So the second term is also coming in the voltage regulation. Okay, so I saw there was one doubt in the chat box. I will address it. And Okay, someone said it's a regulation problem. I did not see. Shashidhar said. Hemalata Padli, you asked, sir, once repeat is current. Could you please unmute yourself and say what was your doubt? I will address your doubt and then end this session. Are you still here?
The first question IS అలా కనుక్కున్నారు కాదు.
First question, which part?
Second part, sir.
Second part. The second
I5
I?
I5 దగ్గర KW ఎలా వచ్చిందో తెలుసుకోవాలి.
Sorry, I can understand you. Just
700 plus 200 ఎలా వచ్చిందో అర్థం కాలేదు.
Sir, is saying about source current, sir, IS.
Source current, okay. Source current is, see, there are two loads. One load is supplying 700, sorry, one load is consuming 700 kVA, other load is consuming 200 kVA. And both the loads are at unity power factor. So basically the load 1 is consuming 700 kilowatt and the load 2 is consuming 200 kilowatt. So the total is 900 kilowatt. And there is only one power source here. So this itself is giving away the 900 kilowatt. And the supply voltage Vs is given 600 volt. So the current will be 900 kilowatt by 600 volt, which comes out to be this.
Okay, sir. Thank you, sir.
And then it is nothing but KCL. So this current we found out. So 1500 minus this I1, this load 1 current will give me the I2. And in the load 2 also, we know the load 2 power, which is 200 kilowatt. We know the load 2 voltage, so it is 300 volts. So from here we found out the load 2 will draw 666 ampere of current. So this branch will be drawing 666 ampere of current. So 723 ampere of current was coming down here, out of which 666 goes away. The rest, which is around 57, that goes in this winding of the transformer.
So can you explain the second problem that first I have audio problem, so that's why I can't listen that one. PSC 16 into 5 into 0.5 like that you second problem.
See, second problem, what they have done is they have done one short circuit test. Okay. And the short circuit test data has been given 16 ampere 0.2 power factor at 5 volt. Now, can you tell me when short circuit test is performed, what power does the transformer draw?
Copper loss, sir.
Rated copper loss. So we have 5 volt, 16 ampere 0.2 power factor. So 5 into 16 into 0.2 gives me 16 watt. So this 16 watt is the copper loss. Now 16 watt loss happens because 16 ampere current flows. Right? 16 ampere current flows. So if I draw let me make some space here. Okay, oh God. I will try to make some space here. Yeah. So if you draw, this is the transformer circuit under short circuit test, transformer equivalent circuit. The load branch can be neglected because the voltage is very low. This is the supply 5 volt and 16 ampere current was flowing. A total of 16 watt was being consumed. So this 16 watt was being consumed in this resistance. So I have I squared R. 16 squared into R in is the 16 watts. So basically I have this resistance referred from the high voltage side, which is 1 by 16 ohm. And from the power factor, I have tan inverse of omega L by R. Let us not write omega L. Let us write X. So this is R1, X1 by R1. This is the power factor angle, phi. What is phi? Phi is cos inverse 0.2. So what do we have? We have tan inverse of x1 by r1 equals cos inverse of 0.2. Everything is known except x1, so we can find out x1. R is known, we have found out. So once we know the leakage impedance of a transformer, we can find out the regulation, right?
Okay, sir. Okay, sir.
This regulation formula you can use, or else you can simply solve a KVL and find out the voltage drop. Anything else?
Nothing, sir. Thank you, sir.
Yeah, so next week, please make sure to watch the videos before coming. You will have three-phase transformers, I think, three-phase transformers and their connection and everything. If you watch the videos before coming, these discussions are also more fruitful for you and me also. Okay, that's all. Thank you. Thank you for joining. I will end
Thank you,
this
sir.
session.
Thank you, sir.